to everyone for joining. It's exciting to actually be here and get to join you all and talk about some of the work that I've been working on the past few years and just kind of get some thoughts in this field. My title for today is just very general here, trying to understand fault failure processes. And particularly, I'll talk about some of my work using physics-based numerical models to try to bridge some of what we know from the lab and what we use field observations to try to say about faulting processes. Um, and please do feel free to interrupt me if I'm going too fast, if you don't understand what's going on in the slides. Um, Please feel free to reach out and ask any questions. So kind of broad overview, kind of the goal of what I've been trying to think about is like trying to assess the conditions that govern motion along faults. So this, as many of you know, is crucial for a wide variety of studies, certainly in earthquake physics and seismic hazards, but also general plate tectonics, crustal deformation, generally how our Earth deforms and moves around. And so the kind of key questions that I look into are what are the factors that control how earthquakes start, where they may propagate, and ultimately how large they can become. What is governing how faults fail from their initiation point through the entire earthquake rupture process. And in particular, I'm interested in large earthquakes, these kind of anomalous events that we don't have that much data for, but are particularly relevant for seismic hazard. And kind of some of the scaling relationships that I look into or insights I look into is how do we use what available information we have from the lab in the field to inform these kind of probabilistic or deterministic hazard scenarios that we would want to look at to, what kind of large earthquakes we might have in California or other major faults along the world, where we might see large slip and potentially compounded hazards like tsunamis, like we saw in the Tohoku earthquake in Japan back in 2011. Um, so stepping back a bit, might be quite boring, but kind of as getting on the same page here when we think about the classical conceptual models we have for the evolution of motion and shear stress and faults. Often think about this kind of generic fault segment in a continuum where we have some elastic medium that is faulted, and the shear resistance to motion is governed by some sort of frictional motion or frictional relationship here. So imagine a Coulomb frictional relationship where the shear resistance is linear dependent on the normal stress on the fault and some friction coefficient. And this fault is essentially resisting motion from tectonic loading and eventually fails during earthquakes. So we often simplify this already fairly simple schematic model into this single degree of freedom spring block slider model where we have compression on a block with some frictional resistance. We pull on the block through some spring that's giving some elastic loading. And over time, the stress built up in the spring will overcome the frictional resistance and lead to sliding. So this kind of model gives us this nice evolution of shear resistance that's quite cyclical in the simple framework here for the spring block slider, where the shear stress loads up to static strength, then during fast motion drops down to a dynamic resistance level. We can imagine that being related to a static friction coefficient, dynamic friction coefficient, and we have failure occurring and sliding going forward. So inherently, these models are quite simple, but also useful because they relate some aspects or physical or material properties that we might be able to infer from the lab or other kind of physical models, such as our friction coefficients here, as well as observables that we get from the field or try to infer from the field, such as the static stress drop or the amount of slip that would happen during a sliding event. And in particular, we get some predictions of what we might expect from those scaling relations. So if we imagine that our static and dynamic friction coefficients are fixed properties, then we see a very clear relationship between normal stress and this Coulomb friction relationship and stress drop, just taking the difference between these two quantities. And so we can make nice predictions that we would use field observations and lab measurements to really constrain the conditions for where failure might start, as well as how much sliding we'd expect to see during these kinds of earthquakes. Um, and so these models, in general, these contribute to a lot of different field observations and lab studies that try to infer these aspects of fault stress and motion, all the way from the lab scale when we're talking about taking, analyzing rock and other material properties, millimeter, centimeter size samples, and doing all sorts of types of experiments to understand their properties and how they are influenced by different physical conditions, environmental conditions, and sliding rates, all the way to field observations of fault stress, such as seismological inversions of earthquakes and heat flow, um, And an important aspect when we compare these two different types of studies is that they're really on a wide different array of scales. So we're looking at centimeter style experiments versus kilometers, at least hundreds of meters scales when we think about typical observations, field observations. And so also there's a wide range of temporal scales when we think about averaging over potentially years of deformation or hundreds of years of deformation, or at least the entire rupture process, versus typically much shorter time scales in the lab. So while we have some more intermediate scale experiments that are coming out around the tens of centimeters and meters to kind of image and understand properties of the heterogeneous motion that occurs during earthquakes, we do have this large gap between what we typically see in the lab and what we get from the field. And that's what I try to explore using numerical simulations, is kind of an analog to these intermediate scale experiments. Um, so jumping in, already when we go and look at the lab, most of what we understand about rock friction and fracture and failure comes from laboratory experiments. And what a wide array of laboratory experiments have shown us is that the resistance to shear motion it's not really a fixed property, but depends on a variety of different properties, including the rate of motion and the history of motion, which I'm sure many of you are familiar here, are encapsulating these so-called rate and state friction laws. So here I'm showing the standard Dietrich-Rhine rate and state friction law, where our shear resistance evolves according to the sliding rate V and a state variable, which is thought to encapsulate the quality and quantity of frictional contacts of a contact population. And what these empirical relationships are really encapsulating are these kind of observations in the lab, as we see on the left, where if we take a frictional interface and slide it at one sliding rate and then jump to a new sliding rate, in this case, a higher sliding rate, we can see this change in the frictional resistance with a direct increase and evolution to a new sliding level where the frictional resistance after this increase in sliding rate is different, in this case lower than it was at the lower sliding rate. And so we can see a rate dependence in the frictional resistance as well as this transient effect here. And if we hold a frictional interface in contact for under negligible motion for a while over different periods, and then try to slide again, we also see the frictional resistance at the initiation of sliding. It also changes. So we see that there's this time dependence or kind of a healing effect that we expect from frictional resistance in the lab. And so these different qualities can be encapsulated into these friction laws that really tells us that there's a richness to frictional resistance that depends on how fast we're sliding and the history of how we've been sliding in the past. And then we can also have an array of different types of state evolution laws to try to describe how this healing could occur and how weakening occurs with slip as well. And I think one of the interesting aspects when looking at these kind of rate and state friction laws is already this notion of a static friction coefficient is not particularly intuitive because under this kind of framework, interfaces that have any type of shear loading are always sliding at some non-zero slip rate. So this notion of static and dynamic failure is not super clear. It's really we're always talking about some rate of failure. We're talking about some notion of slow, some version of fast. Um, so it's just a little bit more difficult to define. But still, this framework is pretty useful because what we can still say in here is there are different types of rates of motion, and what we want to know is how does the shear resistance evolve with that kind of motion. So already when we look at these types of behaviors, we can categorize, in some materials and conditions, we see that as we slide faster, we see this reduction in resistance, so-called velocity leaking behavior, that could potentially lead to unstable sliding. As you weaken more, you slide faster. As you slide faster, you weaken more, and you just kind of have a runaway effect. And in contrast, you have other conditions where you might have velocity strengthening response, where as you slide faster, you strengthen or have higher resistance, and so you promote more stable sliding. And these qualities have been very useful when we try to go out and look at field observations, particularly explaining variations in what we see for fault coupling. So as we go out and use geodetic observations, looking at regions that appear more stuck or slowly slipping, we can actually have this kind of mechanical interpretation of these areas that are locked or coupled and are accumulating strain are velocity weakening and are locked in between earthquakes, but those are also areas that might be seismogenic where earthquakes would occur, whereas areas that are slowly creeping or decoupled can be velocity strengthening and promote stable slip and may actually act as barriers to earthquakes. And that's also fairly consistent with some of the observations for the environmental conditions, such as um, transitions between low compression and high temperature at the shallower and deeper extents of fault zones, and consistent behaviors of velocity strengthening response in the lab. So this has been an incredibly convenient framework for trying to understand what areas of faults, what conditions would promote unstable behavior where earthquakes could occur, and where they may be arrested or where they would be less likely to occur. Um, but more and more over the past few decades, we've been seeing an increasing number of laboratory experiments that really indicate that this standard rate and state friction picture is not the whole story. So in particular, as we've seen experiments push to higher slip rates, so the typical rate and state measurements that we were showing there are often occurring at the, micron, millimeter kind of slip per second slip rates here, where we see friction coefficients still fairly more in line with Byerlee values of friction around 0.6 to 8. Um, but as we see experiments pushing to higher slip rates around centimeters per second, more consistent with earthquakes, we see this dramatic reduction in shear resistance during sliding in the lab. And there are multiple theoretical arguments for why this could occur. There's certainly multiple mechanisms that are seen and proposed in the lab as well. Many of these mechanisms have also been argued to be thermally induced, such as flash heating, thermal pressurization of pore fluids, which I'll be talking about today, thermal decomposition of the fault gouge. But essentially, there are a wide array of potential physical mechanisms that become activated as we start to slide faster, particularly relevant for earthquake slip rates, that just change the picture of what we see for frictional shear resistance, and where we see this dramatic enhanced weakening. And so, just to give a little bit of an illustration of this for those who might be less familiar, one example of a potential mechanism that I use a lot in the modeling and has been proposed in different works is the shear heating and thermal pressurization of pore fluids. So, kind of to give an idea of this, you can imagine that under high loading on faults, you can have relatively high shear stress. As you start to slide faster, you generate shear heating, so friction-induced shear heating, that would increase the temperature along the fault, depending on how localized your fault gouge is, your shearing layer is, and how efficiently heat can escape. And then that rapid change in heat can also lead to trapped fluids within the fault gouge to rapidly expand or pressurize. And then depending on the rock permeability and how quickly those fluids can escape, you would see this rapid shear heating and pressurization of the fault fluids that would basically unclamp or reduce the effective normal stress along the fault, resulting in this dramatic reduction in shear resistance. So this is just one of these kind of proposed mechanisms that can be activated at higher slip rates and higher shear stress. But the main point that I want to explore and kind of talk about more in this talk is that this, these types of enhanced dynamic weakening that we see qualitatively alter some of our models and what we think about for shear resistance during sliding, particularly earthquake sliding, and particularly what regions of faults may be prone to failure during earthquakes. So one result of this, for instance, as shown here in this plot for thermal pressurization at least, is that you get the stronger feedback between motion and weakening behavior, whereas that spring slider model had this notion of a fixed static and dynamic resistance level. And even for standard rate and state friction laws, we see this logarithmic depends on sliding rate, so kind of a more constant friction under fast sliding. As we have this continuous slip occurring with thermal pressurization, we can also produce more heat, which leads to continued weakening. And so our actual shear resistance during sliding continues to decrease as we continue to slide. So there's no real notion of a fixed dynamic resistance level anymore. But it's really process dependent or depends on how big and how much sliding that we see during the earthquake. The other result that has been explored is that we now have this potential for a phase transition between stable and unstable responses to sliding. So in this notion of velocity weakening and velocity strengthening friction, I've shown here in this red and blue for these two different diagrams. We can imagine the shear resistance for velocity weakening materials weakens with increasing sliding rate. If we imagine some thermal pressurization at a certain sliding rate where you activate this rapid weaken, you would see this dramatic reduction in weakening, leading to even more unstable slip. But in particular for velocity strengthening materials, such as clays, potentially that also might be more prone to thermal pressurization due to lower permeability. You can imagine that under sufficiently low sliding rates, they can be velocity strengthening and be stable. But if kicked above a certain sliding rate, they actually would transition to become unstable and dramatically weaken due to thermal pressurization. So we'd have this phase transition in terms of what kind of behavior we'd expect from more stable sliding or stable resistance and sliding to dramatic failure. And this was explored in numerical simulation, showing that indeed, if you have these two different kind of velocity weakening, velocity strengthening segments, you can have these stable creeping segments that are velocity strengthening under slow sliding, but when kicked by an incoming earthquake, they can dramatically fail at higher sliding rates and become destructive. So just because it's stably creeping doesn't mean it's not going to fail in the future. Um, so this becomes a greater challenge for how we use those models beforehand to interpret different types of observations. Um, in particular, while we have an array of different geophysical inferences that we use to study earthquakes and fault physics, many of them, such as earthquake properties like static stress drop, and kind of other earthquake source observations tend to represent average quantities. And even when we look at things like fault coupling, generally speaking, they often have some sort of model dependency for how we interpret them. So a lot of what I'm trying to look at right now is, this kind of work here is to review our underlying models and understand how do we interpret these types of remote observations that typically represent average or integrated quantities taken far away from the source in terms of local fault physics and particularly future earthquake behavior. Um, so as a brief overview of kind of the process here before jumping into actual results, what I'm going to be talking about today is all looking at numerical simulations of earthquakes and trying to use these numerical simulations of a continuum fault model to generate earthquake source properties that we can analyze and connect back to the physics that we put in. So essentially our starting point is taking these lab-derived friction laws, such as rate and state friction, as well as some description of enhanced dynamic weakening like thermal pressurization. We put that in a continuum fault model here, like this very simple generic strike slip fault model. And then we have the elastodynamic equations of motions with full wave mediated effects during dynamic rupture. We also in these models are calculating the evolution of temperature and pore pressure due to shear heating. And then the kinds of models that we'll be looking at today are these so-called simulations of sequences of earthquakes and aseismic slip, where we take this fault model and we try to simulate not just a single earthquake, but hundreds or thousands of years of both slow and fast slip behavior over earthquake sequences. So that's what's being shown here in the movie on the left, where you can see the different colors are showing the log scale of slip rate from the blue, black area being the region of the fault locking in between large earthquakes, the blue being this tectonic loading rate around 10 millimeters per year that we prescribe, and the warmer colors are showing the spontaneous nucleation and dynamic rupture propagation of earthquakes. Oop. And then the ultimate goal of this work is to simulate these sequences of earthquakes, generate catalogs of earthquakes where we can then analyze their distribution of fault slip and stress and their source properties with respect to the physics that we put in. Um, so these are relatively simple models in the sense of we'll use uniform frictional properties, um, but trying to understand how we relate the specific ingredients that we put in here in terms of fault friction and in dynamic weakening with the ultimate source properties that we can constrain. Oops. So this is a bit of a complicated slide, but just to break down how these simulation outputs look. What I'm showing on the left is the evolution of slip. Here, these contours are showing the evolution of slip during individual earthquakes, contoured I think this is every second, for three different earthquakes of different size in the same simulation. And on the right are the shear stress distributions along the fault. So if you take a transect across the fault interface here, on the right is showing the shear stress in gray before and in blue after each of these individual ruptures. And so the simulation I'm showing here is a relatively simple model where we assume uniform physical properties or frictional properties and normal stress within the seismogenic part of the fault. So the model is set up where we have a velocity strengthening region with a velocity weakening area in between where earthquakes occur. That's what's shown basically in these regions here. And one of the key components I want to highlight here is while we prescribe uniform frictional properties, the models themselves with this rate and state friction law end up generating a lot of heterogeneity in shear stress and motion just due to the nonlinear relationship between motion and shear stress in these friction laws. And so what we see is that all these three earthquakes are nucleating in these areas here in purple. There's this finite region where the fault is reaching relatively high shear stress near what's in orange here, the quasi-static strength of the fault. And these are areas where the earthquakes are nucleating, and they propagate over these different gray shaded areas representing the rupture area. Um, and they are propagating over areas of spatially variable shear stress and also leaving behind spatially varying shear stress. And so this shear stress here in these fault models is coming from the heterogeneity in the motion that occurs through the sliding rate, as well as the state variable and changes in pore fluid pressure within these models. But otherwise, all the frictional parameters here are spatially uniform. And so we can see here this moderate sized earthquake starts in an area that nucleates relatively high, propagates over relatively low stress, and the blue here is showing the residual stress that's left after the earthquake, which then is seen the next earthquake here is small and confined within a relatively small area. But the future larger earthquake that nucleates in the same area propagates and actually uses the residual stress here in gray, shown consistent with the blue left from the previous earthquakes, to kind of propagate over the lower stress areas throughout the entire fault here. So what this is indicating is that earthquakes are basically modifying the stress state within the model itself, propagating over spatially varying conditions, and leaving stress conditions for future earthquakes to either arrest or continue propagating forward.
And
Um,
sorry, it's Chris. Can you just tell us these plots on the right-hand side, those are averaged over a small range of depths, or they're just one depth, or whatever?
So this is a 2D model here. So this is a 1D. You can basically imagine that there would be a transect. So it's essentially infinite. The fault would be infinite in one dimension here. Not so much average, but yeah. So there's a
Okay,
1D fault with one dimension off for wave motion, basically, or fault
gotcha.
normal. Yeah. So yeah, the key component here is that while we don't prescribe any material heterogeneity, the variability in the history of motion during ruptures is itself resulting in heterogeneity naturally evolving in these simulations. And so this is essentially one of the key components, and actually the main component that I want like take away from this talk that relates to everything else is that what we ultimately see is that earthquake ruptures really rely on some heterogeneity for how they begin, grow, and stop. And particularly the conditions that we see for rupture nucleation can be quite different from those for rupture propagation. So if we look again here at a single earthquake where the earthquake nucleates and then propagates out, we can look at the average slip for this rupture and average stress drop for this rupture, somewhere around 1 meter and around a 3 megapascal stress drop for this entire rupture. But if we look at three different points throughout the rupture, consistent with the nucleation, center of the propagation, the arrest of the rupture, the behavior is quite different. So where the earthquake nucleates, the stress conditions initially are actually quite high around the quasi-static strength, and it weakens. And you get this relatively high stress drop compared to the average stress drop, basically 6 megapascal versus around 3. Whereas if we look in the center of the propagation, actually the where the earthquake propagates and arrests, the stress conditions are actually much lower than the quasi-static strength. And that's because they're driven to failure dynamically by the waves, the stress concentration at the rupture tip from the history of motion in prior in the rupture. And then it weakens, and actually in this case, for a propagation point, it slips further, but has a lower stress drop than in the nucleation region because of the lower initial stress. And then where the rupture arrests, there's actually a negative stress drop because the final stress is higher than the initial stress that's much lower. And so an
Vale-
important point, yes,
Valere, can I
yes.
ask you a clarification?
Hmm.
So I understood well, the nucleation is only governed by right state, correct?
Mostly,
And
yes.
thermal pressurization is only occurring when rupture nucleate is propagating and therefore slip velocity increase.
So that's not it's not binary. It's not that the thermal pressurization is not active, but it's not dominant. So during earthquake nucleation, most of the nucleation process is governed by rate and state friction. There is thermal pressurization present, but the slip rates are generally not high enough during that process to create substantial thermal pressurization. So you can see here at the initial phase, eventually this point in the nucleation does experience thermal pressurization, which is leading to this more complicated weakening. But the initial phases of nucleation are governed by rate and state friction under the relatively slow sliding rates. The thermal pressurization becomes more active around centimeters per second or higher. Mhm.
Thanks.
Yeah. So that is a key component is that this variability that we see here is certainly enhanced due to thermal pressurization. Although I will say in our models without thermal pressurization, you still see this qualitative behavior where nucleation occurs at relatively high stress conditions once you reach the quasi-static failure conditions. And because of that stress concentration driving rupture propagation, you generally have lower stress conditions for propagation and arrest. Um, and so the key component here is just these different phases of the earthquake, nucleation, propagation, growth, and arrest, have different styles of motion and stress evolution. And when we look at these average properties like stress drop, we're really looking at the aggregation of all that behavior into one. Um, so this brought us back handful of years ago now when we were trying to think about the effects of thermal pressurization and different types of earthquake source properties. So one of the key questions that we had was whether enhanced dynamic weakening is consistent with a very popular trend, which is that there's a lack of magnitude dependence of earthquake static stress drop. That's shown here on the top, where there's a huge scatter when we look at earthquake stress drops, orders of magnitude, but generally speaking, when we look across large populations of earthquake stress drop estimates, there's no clear systematic increase or decrease with the size of the earthquake. And typical popular values tend to fall between 1 and 10 megapascal. And this seems largely inconsistent with this idea of continuous weakening, because if we imagine that we have a smaller earthquake that slips a small amount, we get a certain drop in stress. But if we continue to weaken in larger earthquakes, then as we slip more, we'd expect that stress drop to increase. So larger earthquakes should weaken more, should therefore have larger stress drops than smaller earthquakes. That's kind of the intuitive view that we would have with thermal pressurization, and that would be inconsistent with what we're generally seeing in the field. And what we end up seeing, actually, if we look at models with thermal pressurization here, on the top, this is showing the average stress drop for an array of earthquakes in two different models, shown by blue and red here, as a function of average slip. So this is over a decade of average slip or 3 decades of moment equivalent. And what we see is that we basically get nearly magnitude invariant stress drops for these fault models with thermal pressurization. Here, up until the point the earthquakes with the stars are the largest earthquakes actually are forcefully arrested by the boundaries of the fault model. So that's a little bit more complicated. But if we look at earthquakes here, the smaller to moderate earthquakes that arrest within the velocity weakening regions of our fault, we end up seeing that the actual variation in stress drop with increasing slip and size is not particularly remarkable. And the reason what we end up seeing is that, indeed, as shown here on the bottom, this is the average shear stress in black at the end of the rupture, so average over the rupture area at the end. And in yellow, this is the pre-stress or the initial stress before the rupture. And so what we see is that indeed with thermal pressurization, as the earthquakes are slipping more and growing larger, they weaken the fault more and result in lower final stress. But they also end up having lower initial stress. And kind of remarkably, these actually are, when we look at the difference, it ends up being more or less consistent. And so it's compensating for each other. And essentially, as earthquakes weaken more, they reduce the final shear stress or the shear stress on the fault at the end of the rupture. But they also drive the rupture further onto areas of lower average initial stress. That when you look at the difference, ends up resulting in remarkably nearly magnitude invariant stress drops. So in particular, the earthquakes here are nucleating in regions of relatively high stress, but propagating over areas of much lower pre-stress and arresting over those regions. Um, so the conclusion from all this is really to say when we're looking at these kind of average quantities like stress drop, we have to take into account these finite fault effects that we're not just looking at the single point process of how the earthquake is starting and weakening, but actually how it's growing and arresting as a whole. Um, and so kind of as a conclusion of this, our intuitive view would be that as we weaken more, as we weaken more with slip, we'd have a larger stress drop, assuming that we have the exact same initial stress conditions. However, what we're seeing here as a possibility is that the stress conditions for larger earthquakes, for the initial stress conditions for larger earthquakes could be actually quite different from smaller earthquakes, where certainly you weaken more, but you actually start at a lower average initial stress over the entire rupture area because you're driving the rupture over areas of lower initial stress. And remarkably, in our models, what we end up seeing is that the stress drop can actually be quite comparable despite this completely different weakening behavior in stress conditions on average. Um, and so this result is actually something that we've managed to see over a wide array of different types of models, where what is shown here, this is the average pre-stress normalized by the quasi-static strength. So here around 1 would be earthquakes that are basically occurring around the static strength. And the x-axis here is the size of the earthquake, so the rupture length, normalized by the nucleation size. And these colors are representing different fault models with different efficiencies of enhanced dynamic weakening, ranging from fault models that are just rate and state fault models with no thermal pressurization to more efficient weakening here in red. And what we see is that larger earthquakes systematically occur in these models under lower average stress conditions. And that's particularly more prevalent as you have more efficient fault weakening. So the stress conditions that the average stress conditions governing the rupture occurrence depends on both the size of the earthquake as well as how efficiently that shear resistance is weakening with slip. So here we can see for rate and state friction, you actually also see this decrease in average shear stress conditions with increasing rupture size. It's not that particularly remarkable, but as we increase the efficiency of thermal pressurization, larger and larger earthquakes are propagating under lower average stress conditions. Where if we thought about this in terms of an apparent friction, they can be somewhere around, a average friction of zero point 0.3, even though the actual quasi-static failure conditions here are around Byerly values around zero point 0.6. So these large fault areas can appear to be under stress with respect to quasi-static failure, but these are hosting earthquakes here. So each of these dots is an actual earthquake. The earthquakes are just happening under much lower average stress conditions compared to their static failure conditions. Um, so I want to take a brief second here just to summarize this point so far. Key point that I would like to just kind of,
Valere, sorry
yes,
again. Can
yes.
you can you better explain the physical meaning of this stress ratio that you have on the ordinates? So it should be similar to the strength, no? To the
This
strength parameter, because it is just the ratio of the initial stress divided by the residual stress, more
So
or
you're
less.
saying the left axis, the left here, right? This average rupture pre-stress
Yeah.
versus, yeah. So I would say that the denominator here is what people would often call the strength, right? So this would be your notion of your static failure condition, right? If you were to take, very slow slip rates or steady state at, your plate rate kind of notion, this is essentially your nucleation stress. So when you have this ratio is 1, when the average pre-stress this is averaged over the entire earthquake rupture size. Um, and so what we see here on the smallest earthquakes around the order of the nucleation scale, the average pre-stress over that entire rupture area is near the static strength, essentially, right? You're nucleating over your static strength area.
But
Uh,
therefore, this
mhm,
parameter depends on averaging. And,
exactly.
and you consider the stress as a parameter associated to a single event. You don't resolve the variability of the stress around because you are averaging. Therefore, you model the different earthquakes, but you associate a single number to an earthquakes. There are not the real stress in. So in any case, it depends on averaging, correct?
Exactly. So what we're doing here is we resolve the distribution of stress, and then you have to perform some sort of averaging, exactly as you're saying Here I'm showing a very simple spatial averaging. Although we can also, if you look in our paper, we use different types of averaging for this. You can average it based off of the slip-weighted averaging to be consistent with energy partitioning. And you get the same general trend here. But yes, exactly as you're saying, this depends on how you average the stress along the fault, the stress distribution throughout the entire rupture process.
Right.
Um, yeah. But yes, exactly to that point of if we look, and this is kind of the key point, is if we look around the nucleation size, this ratio here really shows that the average stress over the entire rupture area is consistent with that quasi-static failure condition. But as we go to much larger ruptures that grow considerably larger than the nucleation size, the average initial stress over the entire rupture is less dominated by the nucleation conditions and more dominated by the rupture propagation conditions. And that's really what I kind of want to drive home here is that one, the conditions required to start the earthquake can be completely different from those required for it to continue propagating, particularly as we have more efficient weakening during slip. Um, and then when we look at these earthquake source observations like stress drop, we're really reflecting this kind of average over the rupture process, the average from the beginning to the end. Um, and in particularly as we look at earthquakes that grow much larger than their nucleation scale, so the scale at which those quasi-static failure conditions are governing, our scaling relationships can be more dominated by more heterogeneous propagation conditions, right? Um, and so for these larger earthquakes that are grow considerably larger than their nucleation scale, our differences in stress drop, all of our scaling relationships are more reflective of propagation conditions than nucleation conditions. And that's what we saw in terms of our thermal pressurization result, where we get nearly magnitude invariant stress drops in these kind of models. Um, I don't have time to really get into this today, but I do want to point out again that this difference in stress conditions, most of what I'm talking about here relates to thermal pressurization, but the difference between nucleation and propagation also is observed in rate and state models without enhanced weakening. It's just not as remarkable here. But one of the things that a grad student I've been working with, Minhyun Yan, who just published this paper looking at normal stress dependence of stress drops, has also found that while there still is a relationship, actually, we see here in terms of magnitude dependence of stress drop and normal stress dependence on fault weakening and stress drop, this difference between the reflection of more heterogeneous propagation effects in these models that are much larger, earthquakes much larger than the nucleation size, can also result in altering other expected scaling relationships. So in particular, what he sees is there's actually a weaker sublinear relationship between average earthquake stress drop and fault normal stress, even in rate and state models when we look at earthquakes that are much larger than the nucleation size. So happy to talk about that a little bit later. If you're interested, you can look at that paper there. But kind of the same effect that when we start to look at conditions related to larger earthquakes compared to the nucleation size, we're really looking at this averaging over heterogeneity that's not as reflective of static failure anymore, as much as propagation effects. Okay, let's see how am I doing in time. So I want to jump into the second part here, which is more focused on where can earthquakes actually propagate, or how do this weakening behavior affect where earthquakes can propagate? Um, so coming back, one of the points that we also saw here was this efficient weakening uh, in fault models can lead to large earthquakes drawing the average stress state along the fault much below conditions for rupture nucleation. So if earthquakes nucleate at this relatively high stress, as we have larger earthquakes occurring with more efficient weakening, the average fault conditions actually are much lower than conditions for nucleation, making it harder for earthquakes to actually start. But also, this more efficient weakening, it makes it more favorable for earthquakes once they do start to grow under these lower, less favorable stress conditions. And so one of the things that we also see in these models is that we have a different relationship between the sizes and distributions of earthquakes depending on the efficiency of weakening. So in models with relatively mild weakening, we see that the heterogeneous stress conditions that naturally arise can result in a wide distribution of earthquakes. This has been explored in a variety of different models, where we have more smaller earthquakes and relatively fewer larger earthquakes. But as we increase the efficiency of weakening going to the right here, what we end up seeing is that it becomes harder for smaller earthquakes to nucleate, and we tend to see much larger earthquakes, or we tend to see more larger earthquakes compared to smaller earthquakes. So essentially, it's easier for any individual earthquake to just become much larger and harder for individual earthquakes to nucleate. Um, Another way of kind of looking at this, so here I'm showing three different simulations. And this is going from left to right with increasing efficiency of weakening. The orange here is showing that nucleation stress condition, that quasi-static strength, and the black here is showing just the spatial average of the shear stress over the entire seismogenic fault zone. And the bottom is showing the distribution of earthquakes in each of these fault models. And so what we see is that as we increase the efficiency of weakening along the fault, we are dropping the average stress condition along most of the fault, so that the fault is on average operating further away from failure. Oh, do I have my own hand raised? Oh. Um, and so what that ultimately leads to is it becomes increasingly harder for smaller earthquakes to nucleate. They do nucleate, um, but much more infrequently. And generally speaking, we just get larger earthquakes that are occurring under these lower average stress conditions. And so essentially what this is showing us is that the frequency magnetics that we've seen can also be sensitive to the fault weakening behavior along the fault, and particularly how it influences the relationship between the average fault stress conditions and the nucleation conditions for the fault. So more efficient weakening leads to, in this case, all three of these models have actually all the same normal stress, like the absolute stress conditions and quasi-static failure conditions. The strength of the fault is actually the same in all three of these models. But the efficiency of weakening leads to lower stress conditions for more efficient weakening, which leads to more larger earthquakes compared to smaller earthquakes, and essentially an equivalent lower B value compared to fault models with more mild weakening that are more sensitive to all these types of heterogeneity here. Um, so what that's basically telling us that the frequency magnetics are not just dependent on the absolute stress conditions, but in this case, the actual weakening behavior that changes the relationship between the fault stress conditions and nucleation conditions. Um, and particularly a key takeaway.
Valere,
Yes.
would you mind going back to that slide? This is kind of an interesting result. It seems like it's more though than your result implies more than just a change in B value though.
Hmm.
Did you care to comment? Because in this sense, it's if you look at the far right distribution, it's essentially pulled away the occurrence of any of the smaller events in
Yeah,
this.
exactly. So, and there's a certain point here. So one, I throw in the caveat of like interpreting these distributions as a b-value is a questionable term, right? Because we're looking at small numbers, and whether this is actually following a power law is a whole other question, right? A much more robust term is just exactly of what you're saying there, as we get more larger events, fewer smaller events. Part of that limitation is that we're using a 2D model here with no prescribed heterogeneity in it as well. Um, but exactly to your point of essentially we see the suppression of small earthquakes as a whole. We still see some small earthquakes. They just happen much more like much more rarely or infrequently. Um, and another point that one can kind of put into this is like if you had other forms of heterogeneity, um, they would have to kind of be measured with respect to this weakening behavior also. Then you might promote some smaller earthquakes, but they would have to be measured with respect to this efficiency of weakening. But I think to your point, this is not really following. I don't know if it's a particularly robust way of interpreting this in terms of B-value changes, as much as just fewer smaller events are more likely to have larger events at the expense of smaller events, if that makes sense.
Okay, no,
Can I
fair.
ask on,
Thanks.
sorry, can I ask on the same question? I don't
Hmm.
understand these figures. I mean, why do you even nucleate at all and why only large events?
Yeah, so this is the complication here is actually in terms of this black line here is showing the average stress over the entire fault region. So if we come back all the way here, this is actually taking the average over this entire region. Hopefully you can see my cursor. And so the key point here is that there are still parts of the fault that, particularly at the edges where the loading rate is higher, where they do reach high stress and they nucleate earthquakes. Um, But then there are 2 points of it. One is that because the stress conditions end up being low throughout most of the fault, it just takes longer for you to actually be able to nucleate an event. The other point is that once you do nucleate an earthquake, in these relatively high stress regions and they start to propagate, because of the more efficient weakening, they're able to continue growing over the low stress areas. It's basically the fault is already critically stressed for propagation, so they just continue to grow and basically break through the entire fault. Because that more efficient weakening drives the earthquake propagation over it. Whereas with more mild weakening, it would arrest due to lower pre-stress conditions. Does that make sense? So in these models, all of these small jumps here are smaller earthquakes where the actual local stress is closer to this orange line. It's just that, more consistently in the line here, when it actually reaches the top here, these are the largest earthquakes, and all these are smaller earthquakes. So maybe this is not the best way of representing this. But the main point is that the smaller earthquakes are happening in areas of locally high stress at the edge of the faults. And this is just representing the average over most of the fault that's further away from failure, which is why these smaller earthquakes don't continue to grow. Did that help or maybe not?
No, no, I think it does. I don't know. They'll
Okay.
they'll keep talking if they have more questions.
Okay.
We'll wait for
Sounds
them.
good. The main component that I wanted to bring around here, I think also to the B value question is more of the point that essentially as we see these fault models with more efficient, when we have more efficient weakening in these fault models, what we end up seeing is a suppression of microseismicity, in part because once an earthquake nucleates, it just grows and ruptures the entire fault. And so our fault models with more efficient weakening show diminished microseismicity, which is an intriguing thing to compare to some faults in nature that have hosted large earthquakes, but are generally lacking in microseismicity today. So one example is the central section of San Andreas Fault, where we have had the 1857 large earthquake in the center part of the Carrizo segment, which currently today has some microseismicity, but is fairly quiescent overall. And so this may indicate that these kind of areas that we know have had large earthquakes are seismogenic, but are currently seeming to be quiet. That may actually be observational indication that the stress conditions are just below failure conditions for most places along the fault, right? Some areas might be nearby, but most of the fault is actually below conditions for failure or for quasi-static failure, nucleation conditions. However, that doesn't inherently mean that the fault is not sufficiently stressed to host a large earthquake once one of those points actually does trigger an earthquake. So this is a potentially, if that's actually true, that this paucity of small events on these mature faults is an indicator of this kind of a more efficient weakening that draws down the average stress state, that could be potentially useful physical motivation for improving our, earthquake early warning systems or probabilistic seismic hazard, because we wouldn't expect the probability of any earthquake growing much larger to be governed by your typical Gutenberg-Richter statistics, right? In fact, these might be much more characteristic faults where once any earthquake nucleates on them, they just grow and rupture the entire region. So that's an interesting thing to delve into a little bit deeper, where maybe some of these mature faults that host large earthquakes and are silent in between really is an indicator of operating with some different physics where there are well-defined fault zones that undergo extreme weakening during rapid slip. Um, and another area, this last topic that I want to get into here, talking about another area of seismic quiescence, is looking at Cascadia, another major fault zone that is fairly quiet, but there's a wide array of geological evidence suggesting that it has had large earthquakes in the past, and trying to understand what is the relationship between that and potential enhanced weakening during great earthquakes. Um, and this has just been a topic that I've been interested in for the past few years. So one of the key questions for Cascadia is that we have a large subduction zone that generally doesn't have earthquakes on it, And a key question is, what is the depth extent to which a large earthquake in the future could potentially propagate? So one of the key observations for Cascadia is that while there are no earthquakes, there are these regular slope events that happen near the depth, the deeper extension of the fault zone, particularly going down closer to Seattle and Portland. So the major question is, could a large earthquake propagate down into these deeper extents? Or are they limited by our typical notion of fault locking, shown here in color in the different colors, based on where we expect strain to be accumulated. So generally, the broad question here is, how do existing observation of slow slopes tell us anything about the physical conditions at depth? And I won't get into actually the answer for this as much as this broader notion as what does fault coupling actually tell us about seismic hazard? So, you know, kind of painted the picture at the very beginning that this notion of rate and state friction and velocity weakening, velocity strengthening has been very convenient for talking about spatial variations in coupling behavior and where earthquakes would occur, where locked segments, maybe velocity weakening, potentially unstable, particularly if the area is large enough compared to the critical nucleation scale for earthquakes um, to host earthquakes. Whereas stably creeping, slowly slipping areas maybe or that are decoupled, have lower coupling, maybe velocity strengthening. They favor slow slip and potentially act as barriers to earthquakes, or at least are not accumulating strain that will be a release during earthquakes. And then over the past, few decades, there's also been these observations of not purely stable creep, but actually slow slip events. So more episodic, slow events that are faster than plate rate, but still not seismogenic. And there's been a wider range of different models that have tried to explain or generate slow slip events, often involving some form of heterogeneity. So particularly these are widely consistent with kind of the schematic here that we imagine for a subduction zone, where you can think about your typical seismogenic zone as you go to deeper extents or shallower extents where you see more stable or transient slow slip. You might have these transitional regions with special heterogeneity, be it frictional heterogeneity, roughness, or some transition stabilizing mechanisms like gauge dilatancy for fluid effects that ultimately lead to more stable behavior. And in some of these models, the critical heterogeneity might lead to a slow slip event becoming an earthquake. Sometimes they never do. But there's this general idea of while they're actually slow, they might be releasing some of that strain that would be otherwise occurring. The strain release would occur during earthquakes and therefore might be limiting seismic hazard. Um, and kind of tied into the notion of what does the stability of these slow slipping regions mean, we once again come back to this idea of enhanced dynamic weakening. And while an area could be could be stable under slow slip, if it's kicked or somehow triggers dynamic weakening, it can catastrophically fail. So ultimately, coming back to this question of how do we relate slow and fast slip, particularly in this paradigm of dynamic weakening and the differences between conditions for slow failure and fast failure. Um, so here, just for those who are not familiar with this work by Hiroki Noda and Nadia Lapusta, I'm kind of building off of this model here where we imagine two simple segments of a fault. One is velocity weakening, one is velocity strengthening, but more prone to dynamic weakening. And the idea is that when an earthquake nucleates in this typical seismogenic zone, it can break into the region that is more stably creeping. This last model that I want to talk about today is built off of this, trying to look at the relationship between slow, particularly slow slip events, and fast slip. And so we imagine that we have a patch that is velocity weakening with some mild dynamic weakening that can act due to thermal pressurization, and another patch that is mostly velocity strengthening and so promotes slow slip. But then I include a very small velocity weakening inclusion that is small enough that it will create slow slip events, but it never generates an earthquake itself. So here we'll simplify this further to 2D, but the key point here is that we have one patch that generates earthquakes and one patch that generates slow slip events, but never nucleates into an earthquake. It's more promoting stable slip. Um, and when we look at this model, we can see a rich behavior of different types of earthquake evolution, very consistent with the results qualitatively from Noda and Lapusta, where in this patch A, that's velocity weakening, we generate earthquakes of varying size. They always nucleate in patch A. And then sometimes you can see this large earthquake propagates into patch B, by triggering thermal pressurization. And here on the left is showing the evolution of slip, and red is the seismic slip, and black is the interseismic slip in between earthquakes. On the right is the ratio of the slip rate compared to the long-term slip rate. So you can see in black regions are locked, and the white bars are showing the spatial extent of the earthquakes that are happening on the left. So we see these complicated sequences of great earthquakes that span both patches A and B due to this dynamic weakening breaking through patch B, with intermediate smaller earthquakes in patch A. And the key thing that's different here is that in patch B, after large earthquakes, we don't get smaller earthquakes, but we get, several decades of slow slip here that are actually showing up as slow slip transients if we look at the evolution of the slip rate here. So we get locking leading up to slow slip events with intermediate smaller earthquakes in patch A. So the question is, can we see anything different between this kind of model and where you can see a break into patch B versus if patch B was always just steadily creeping? Um, Zooming into a single earthquake cycle again, if we look after a large earthquake, both patches A and B are going to be locked after the substantial seismic slip. Eventually, patch A starts to have earthquakes again, and eventually, patch B starts to have slow slip events prior to the next large earthquake. And if we examine just the integrated slip here, kind of like an analog for the coupling behavior for 40 years prior to this large earthquake, we would see the integrated slip deficit prior to the earthquake, which shows a substantial slip deficit in patch A, as we kind of expect. That's our velocity weakening area. But in patch B, there's not a particularly remarkable deficit in slip. There's some slip deficit here due to the stress shadowing from patch A. But in this conditionally stable velocity weakening, velocity strengthening area with slow slip events, we're integrating over that behavior, and it essentially looks as if it was creeping, where we see no substantial strain accumulation. But the subsequent rupture that happens here actually breaks into patch B, where we had very little noticeable slip deficit over this 40-year time frame. In fact, most of the slip that occurs during this earthquake happens in patch B, where there's a fairly negligible slip deficit. So this is really just saying that this relatively short-term deficit over 40 years prior to the earthquake is not showing us that much in terms of the overall strain accumulation that's happened over the larger time scale of this great earthquake that is around 300 years here, right? We're quite limited in understanding that full strain accumulation. And what's even more complicated is if we compare this with another model where we had no thermal pressurization in patch B, so we have negligible slip that ever propagates in, and we looked at the same strain accumulation prior to the earthquake, they look more or less comparable, with no particularly remarkable interseismic slip deficit between patch B, whether it breaks in a future earthquake or not. So this is more of a depressing result that just these accumulations of interseismic slip deficits can be useful for telling us something about, obviously if we see a slip deficit that tells us that maybe we're most likely going to see that caught up somewhere in the future. But just because we don't see a slip deficit right now over some decades doesn't mean that that area is inherently safe from future seismic slip. In this case, it actually could undergo, 6 meters of seismic slip in this particular model. So a depressing result, but something that's interesting then is like, well, if SOSLIP doesn't really tell us that an earthquake can't fail, what could it potentially tell us? And this kind of comes back to this relationship between fault stress conditions and nucleation conditions, or just failure conditions. And if we look back here at this evolution over this large earthquake cycle, and compare a point here in the center of our velocity, our slow slipping patch, what we see is that after a large earthquake, both patches are locked, and that's consistent with the patch B here being under stress. So the fault is substantially locked, slipping much below the plate rate, and the fault at that area is substantially under stress compared to the static stress conditions here under the blue line. So this is showing the ratio of the shear stress at this point in the slow slipping patch compared to the nucleation conditions. As time goes by, the fault is continuing to be reloaded. Patch A has these intermediate earthquakes, that don't break into patch B because the fault is still under stress. So you can see these little blips consistent with earthquakes in patch A here. And it's only until later in the earthquake cycle that patch B starts to slowly slip again and eventually start having slow slip events. And that lines up with when patch B has finally been reloaded to static failure conditions and starts to actually slowly slip. And so one of the key points that we actually see in this model is that if we have an area that is prone to slowly slipping, when it actually starts to slowly slip, it really what that tells us is that it's failing about its quasi-static strength. That is the one thing that slow slip tells us. Slow slip is telling you that the stress conditions locally are near quasi-static failure, and therefore it's able to slowly yield about its yield strength. And so in this particular fault model, where you have an area that is conditionally stable, so able to slowly slip either by a steady slip or by a transient slow slip, if it is slowly slipping, it is actually optimally stressed to fail in the future. So when it was under stress and locked, it was accumulating strain, but was not sufficiently stressed to be pushed to fail. But when it actually is fully stressed at its quasi strength and therefore primed to fail in the next earthquake, that's when it starts to slowly slip again. So in this case, the slow slip is actually an indicator, not that the area is it's no longer accumulating elastic strain, but in fact has accumulated all the strain it could potentially hold, so that it's now yielding at its yield strength, which is a completely it's kind of qualitatively different from how we typically interpret local fault coupling in terms of being an area that is relatively safe. Um, so just to bring back some key points from this model, when we think about locking, we typically think about an area that is accumulating strain and therefore potentially seismogenic, which is fair. But in this case, an important point is that locking mechanically here occurs after coseismic slip, and that indicates that the fault is actually still under stress with respect to the static strength. Um, After sufficient loading following an earthquake, a region can exhibit steady or transient slow slip. And what that really is indicating is that the fault is now critically stressed. It's at its yield stress, right? The question is whether it will fail or not, but if it could fail, it is now primed to do so. And the last thing I want to point here is that in this model, the slow slip in patch B occurs because this is an area that never nucleates into an earthquake. Um, but also, if we look in patch A around the nucleation region, we see that leading up to the beginning of any earthquake, you start to see these oscillations or slow slip transients that are essentially failed earthquakes. And this has been widely observed in other numerical simulation rate and state models as well, where essentially leading up to the nucleation of earthquake, you get little oscillations that are essentially failed earthquakes building up. And this is just to say that whether or not a region is able of nucleating an earthquake or not, the presence of slow slip is essentially that observational indication that the region is starting to approach favorable conditions for rupture propagation, regardless of its capability of nucleating the earthquake itself. Um, so I'm at 8:36. I think I'll go ahead and stop here so we have time for discussion. But kind of the key points I want to take away, again, is that really the separation between the conditions for an earthquake to start and those required for an earthquake to grow. And those need not be the same, and particularly not necessarily the same, particularly because of the energy released during an earthquake that drives it forward and therefore results in much different conditions required for ruptures to continue propagating. As a result, these conditions for rupture occurrence depend on the size and weakening behavior. And kind of the 2 points that I really want to bring out here is that because of these differences for rupture propagation, and particularly with efficient dynamic weakening, large fault areas might appear to be under stress compared to earthquake nucleation, therefore not capable of hosting an earthquake. But because of that efficient weakening, once an earthquake starts, it could still be critically stressed to host an earthquake. And actually, the paucity of smaller events on some mature faults may actually be an observational indication of this dynamic weakening during earthquakes. And this last point is that, while fault regions that can appear to be stable and slow slipping, but catastrophically fail under dynamic loading, and so it's kind of hard to tell whether an area as slow slipping will actually fail in a future earthquake. But if it could, the observation of slow slip actually is an indication that that region is sufficiently stressed to be yielding at its quasi-static strength. So if a region is susceptible to failing dynamically, the observation of slow slip would actually suggest it's favorably stressed to fail in a future earthquake. So thank you so much for your attention and your time. Happy to take any questions and just chat here.
There, fabulous talk. I'll invite people to unmute and join me in thanking you for a great talk. We'll give you a second to catch your breath here, and then we can thank Paul Siegel for showing everyone else how to raise your hand and join the queue to be involved in the discussion, to lead the discussion. And Valère, if you're ready, maybe we'll just invite Paul to go ahead.
Yeah.
Fantastic talk, Valère. A lot of things to possibly discuss, but so I sort of struck, you really emphasized in the beginning of your talk that dynamics can lead to heterogeneous stresses, which can be extremely important. But it seemed to be there was kind of a tension between having strong dynamic weakening, which could explain the size invariant stress drop,